Morning. I hope that you have a good break. Now you are completely ready for new lessons and new weeks in front. Okay, do you have any kind of questions before starting? Okay, so today I want to talk about circular permutations and what we call as R permutations. Okay, so let us have a definition. It's very hard to define circular permutation in words if I just want to keep it very not technical actually. So an arrangement of a number of objects about a circle, this circle could be an imaginary circle of course, is called a circular permutation if the order of each object in the arrangement matters, and in the meanwhile, if an arrangement can be obtained from any other arrangements by a rotation, either clockwise or counterclockwise, they are considered the same arrangements. Okay, so that is a little bit different from the permutation we had. Sometimes we call that permutation a linear permutation to distinguish it from the circular permutation. So what is the circular permutation? Is that you can sometimes, for some reasons, we will give some examples of that, of course, you are not very interested in the particular location of an object, but you are caring about the neighbors of that object in that arrangement. Whenever this happens, it means that you are interested in what we call a circular permutation. So for example, consider four objects. Let us consider four letters here. So letter A, B, and C, and D, for example. And then let me consider a circle here. Yes. So for example here, let me just take this one, copy it, yeah, and then paste it here, for example. Yeah, let us keep it here. And then, for example, one particular position is that one particular arrangement of these four objects around this circle, it could be, I said, imaginary, is to put A here, B here, C here, and D here. If I put A here, B here, C here, and D here, of course these are different. Yes? If for example these are people sitting around a round table, okay, if you go outside the room and come back and see this situation, you immediately realize people have switched places. Okay? So what I'm saying is that this situation is recognizable from this situation, but if you say what are the neighbors of this person A, for example, these are B and D, and the point is that, for example, this is on the right hand side of A, I'm just looking into the page, and this is on the left hand side of A. Yes? And so it means that the neighbors of A are the same, and the order that the neighbors appear on the left hand side and the right hand side of A is B on the right, D on the left. Now if you go to this situation, the neighbors of A are still B and D, and then A is again on the right, on the left hand side, and D is on the right hand side of A. So what I'm saying is that even though these two are recognizable from each other, but one of them is obtained from the other one by 90-degree rotation clockwise. Yes, so you see that B has been replaced by A, I don't know, C has been replaced by B, and D has been replaced by C, and finally A has been replaced by D. In the circular permutation, we want to consider these two the same. Okay, whenever you are facing this kind of problems, that the neighbors of each item are important for you, not only the order. Of course, order is important, but this is not the only thing that is important for you. For example, I can have another one, yes. So for example, I can put A here, B here, C here, and D here. This is also the same. And then finally I can have this situation. I can put A here, I can put A here, B here, C here, and D here. So from circular point of view, I am considering all these permutations the same permutation. Okay, so it is clear that I'm changing the positions. So if this location is location 1, this location is 2, this location is 3, this location is 4, now location 1 is filled with D, location 2 is filled with A, location 3 with B, and location 4 with C. So it means that if I just consider the places, different places 1, 2, 3, 4, the first one gives me A here, B here, C here, D here. The second one gives me A here, B here, C here, and D here. Okay, and then you see that this combination, this permutation is different from this permutation with the definition of permutation. But when it comes to circular permutation, we want to consider all these permutations that you see in this picture the same. Okay, and then for example, of course, let me just move this a little bit here. But for example, this permutation here that I want to write, for example, I put A here, I put C here, let me put D here, B here, and C here. Okay, so I would say, of course, this is not a very good way of writing, but let me put equality. I want to consider all of them the same, but this last one is not the same as before. Because now you see that this cannot be obtained by this from any kind of rotation, yes? If I want to rotate this object, it does not happen that D goes here and B goes there and C and A are here and here. So this permutation cannot be obtained from any one of these permutations but any kind of rotation. So I will consider this a new one. So if I ask you how many circular permutations you see in this figure, you would say I see only 2. All of these are counted once and this one is counted once. But if I ask you how many linear or just permutations, how many permutations you see here, this is 1, 2, 3, 4, and 5. Okay? So we want to understand how many circular permutations we can write down. Is there any formula for that, or we should do it case by case? Fortunately, the answer is that there is a theorem for that. You don't need to do it case by case. Okay, and the answer is that the number of circular permutations of n distinct objects is n minus 1 factorial. The number of permutations of n distinct objects, if you remember, was just n factorial. And the reason is clear because, for example, if you are dealing with 4 objects, you see that when you write a new circular permutation, there are 4 of equivalent way of writing that. So it means that if I want to know the number, I calculate 4 factorial, which is just the normal permutation, the number of normal permutations, but I have to divide this by 4, because now each permutation that I write has 4 rotations if I have 4 objects, but these 4 rotations does not produce a new object for me, a new circular permutation for me. So the total number of circular permutations is not 4 factorial, is 4 factorial divided by 4. But I can write it as what? I can write it as 4 times 3 factorial divided by 4, and then 4 and 4 are gone. So you see that instead of having 4 factorial, I will have 3 factorial. And it doesn't matter if I have, for example, n objects. When I have n objects, then I have n factorial linear permutations. But now assume that they are arranged around a circle, and then there are n names for each one of these, yes? So this means that I can divide this by n. The answer would be n times n minus 1 factorial divided by n. So it would be n minus 1 factorial. Yes? So this is the way that you count the number of circular permutations. I told you that just this table or whatever is circle can be imaginary. Whenever you are interested in a permutation in which the neighbors, not only the order matters, of course, but if one permutation, each person has the same neighbors, then these two permutations are considered to be the same. If this is the case, then you are facing a circular permutation. Okay, now let us solve some problems. If you have any questions, please let me know here. Yes, please. Hello. I cannot hear you properly. Your microphone is probably...
Oh, okay. But the last one is the same as the first one. So why isn't it?
No, it is not the same.
Why doesn't it count?
No, it doesn't. The reason is that...
Oh, it's not the same.
It's by rotating you should be able to get it. Yes. This one is not this one. Because if I start rotating this object around, I will never be able to get this back.
Yeah, I understand.
Okay, no problem. So let us go to example number 1. In how many ways can 6 people be seated about a round table if what matters is people on the left and right of each person? So usually in combinatorics books, when you see round table or something like this, it means that that problem is actually interested in testing your knowledge about circular permutation. So usually I don't need to add this last sentence or phrase at the end. But anyway, in how many ways can 6 people be seated about a round table? If we just think as normal permutation, and if this sentence is not probably given to you, if I just ask you how many people can sit, in how many ways 6 people can sit in 6 different places, you would say 6 factorial. But now, because what I told you, if you understood what's going on, it means that this problem is interested not in the linear permutation, it's interested in the circular permutation. So the answer is not 6 factorial according to the theorem above. So what we can do, we can write 6 minus 1 factorial. But the answer becomes 5 factorial. And then if you want, you can calculate, and that is 120. Yeah, please, if you have any questions, interrupt me whenever you feel uncomfortable. Okay, now a more interesting example is example number 2. In how many ways can 3 married couples be seated about a round table if what matters is the people on the right and left of each person and that the sexes alternate? So we want to arrange them so that the sexes alternate. Okay, so for example here I have a round table, but I have 6 people here. For example, man 1, W1, so they are married. For example, man 2, woman 2, man 3, woman 3. They are actually couples. But of course, what is important is to write to arrange them around this round table so that the sexes alternate. So how can I solve this problem now? So how, for example? So you are saying that, for example, we have 6 positions. So for example, we have one position here, and then if I can draw it properly, one position here, one position here, one position here, one position there, and one position here. For example, we have 6 positions around this table, so let us think it symmetric. It's symmetric, okay? But then I want to give the men some places. So in how many ways I can do that? It doesn't matter. In this arrangement, it doesn't matter if I start a man here or here or here or here. It doesn't matter, yes? So because that's a circular arrangement. So what can I do? I can say that, okay, I will take these positions and give them to men, and I will take these positions and give them to women. But the important thing is that in how many ways I can put men here. So you don't need to consider these things. So this is a circular permutation. I have 3 objects here. The objects are men. So if I want to calculate that, it becomes 3 minus 1 factorial. So it is 2 factorials. Yes? I cannot have I cannot have more than this. Okay, but now the point is that when I put the men in these positions, for example, so let me assume that I chose this place for man number 3, I chose this position for man number 1, and I chose this position for man number 2. Okay? Now, if I want to put the women here, I am not allowed to use circular permutation. Yes, I have to use the normal permutation. Yes, because if I ask the normal permutation, if I just want to do the circular permutation, so it means that if, for example, if I put W1 here, W2 here, and W3 here, okay, and let me now start rotating just women, okay, not men. Okay, so what happens here? Let me try to draw another diagram for you here. So let me keep man 3 here, man 2 here, man 1 here, and then instead of W1, let me write W1 here, W3 here, and W2 here. You see what is happening? Don't look at the position of men. Are the women distributed circularly here? In a circular way? The answer is yes. You see, I have replaced, I have rotated this in this direction, yes? W1 is now here, W3 is here, W2 is here. So this is coming from this by circular rotation of the position of women, okay? But now consider, is this a new permutation from the previous one? Should I count this once more in this problem, or that is exactly the same? So according to this problem, do you consider this and this the same or not?
No.
Exactly. So that is what I want you to understand. So what is happening is that I am just putting the men in a circular permutation because no one is taking the seats. So I distribute men in a circular permutation. But if I insist to do women in a circular permutation, to arrange them in a circular permutation, it means that I am not distinguishing between this case and that case. But in the problem, we have to distinguish between this case and that case. Yes, because for example, if I ask you what are the neighbors of this man, you would say that the neighbors of this man are W2 and W3. If I ask you what are the neighbors of the same man in this permutation, you would say W1 and W2. So the neighbors has changed. So it means that this situation and that situation should be different. So this motivates me that the second stage of the problem shouldn't be done in circular way. It should be done in normal permutation way. So the problem is that the second arrangement is not 3 minus 1 factorial, it's 3 factorials. Okay, and then the total answer, so the number that is interested for this problem, is 2 factorials times 3 factorials, which is 12 in this case. Is that understandable? So you need to have a good understanding. Just putting people around the round table, it doesn't necessarily mean that we are interested in the circular permutation. You saw that the first arrangement is circular, but the second arrangement is not circular. If you consider the second arrangement again a circular arrangement, so it means that you are not differentiating between this arrangement and that arrangement, but according to the problem we have to differentiate between these permutations, because at least, for example, for this man, the neighbors has changed. Yes? Okay. Now let us go to the next problem. In how many circular permutations, so when I say circular permutations, it means that I am interested in circular permutations, of the letters in the word magnetic are the vowels adjacent? Okay, so how should I solve this problem? Do you have any idea? So let me write the letters. So I have magnetic, so these are consonant, so N and T and C, and the vowels are A, E, and I. So I want to have them in one box, yes? Okay, can you continue and answer this question? I want to arrange them about a circle. I am interested in circular permutations. On top of that, I want to count all those circular permutations in which A, E, and I are neighbors, are adjacent. So how should I solve this problem?
We think of it as a circular permutation with 6 objects.
1, 2, 3, 4, 5, 6. Yes? Yes?
Or one, or the vowels are one object.
So for the first one, okay, you are right. For the first stage, how many circular permutations do I have? You said 6 objects. You are right, because you're counting this as one object. And 2, 3, 4, 5, 6. And I arrange them in a circular way, so it becomes how many factorials? It becomes 6 minus 1 factorials, okay? And then, of course, you also need to consider a permutation for these, because we want to just to keep them next to each other, but the order can be A, E, I, or E, A, I, or I, A, E, or whatever. Okay, what is that number that you want to consider here?
That would be just linear.
Linear, yes. It would be linear permutation, so it would be 3 factorials, and then according to the product rule I have to multiply them. So the answer is simply 5 factorials times 3 factorials. Okay, is that clear? Yeah, I brought this up because I saw some problems in the book related to this circular permutation. Okay, so you need to know that if you want to solve the problems in the book. Okay, any questions? Now we go to another very important topic of the lesson, and that is the notion of R permutation. What is an R permutation? So the idea is very simple, actually. So the idea is that you have n objects, and R is a natural number between 1 and that n. A permutation of these n objects consisting of R of these objects, only R of them, is called an R permutation of the objects. Okay? The number of R permutations of n distinct objects is denoted with one of these symbols. These are the common symbols. This is used in your book. Okay? So the number of R permutations from n objects if the objects are all distinct, is denoted by this symbol P, N, and R, or this symbol or that symbol in different texts. So here I have, for example, 10 objects, but I want to choose 4 of them and arrange them. So let me solve this problem for you. For example, here write down all 2 permutations of the letters A, B, C, and D. By counting these permutations, determine P of 4 and 2. So you see here I have 4 distinct objects. If I want to write all permutations of these objects, you know the answer. The number of them is 4 factorial, which is 24. But here I do not want to write all permutations. I am interested for some reason in 2 permutations of these. So it means that you need to choose 2 of them at a time and still arrange them. So for example, I can choose A and B, but still I need to arrange them. So there are 2 ways to do this: A, B, or B, A. Or I can choose, for example, A and C. So let me clean this, we don't need that. Okay, this is one possibility. One possibility is that I choose A and C. So then there are 2 ways of arranging them. So not only I have freedom in my choices, I also have freedom in how to arrange them after I have chosen them. So this is very important, that when you write this, you are counting all these items that I am writing down, if the objects are all distinct. Okay, so the other possibility is CA. I can also have A with D. Yes, then I will have also D and A. Then I can have B and C, and then C and B. Then I can have B and D. Then I can have D and B, and finally C and D, D and C. I hope that you agree with me there are no other 2 permutations of these 4 objects. And then if I have done my counting correct, my writing correct, then counting is very simple. 1, 2, 3, 4, 5, 6. 6 times 2 is 12. So this motivates me that this number is 12. Okay, of course, it's clear that in combinatorics we want to come up with this answer without having to go through writing them down. Okay, so we want to find a formula for getting this 12 immediately without writing down all the permutations. Any questions? So you see, still order matters, but not only order matters, the choices also matters here. Okay, write down all 2 permutations of these letters, 3 A's and 2 B's. Again, I have 2 permutations, but I have 3 objects identical, all of them are A, and 2 objects B, all of them are identical. So how many 2 permutations I can write here? So one possibility is that I choose 2 of them be A's, yes? So one possibility is A and A, and for arranging 2 identical A's, I have only one possible scenario, so that is just A and A. I can choose 2 B's, so that's B and B. I can choose 1 A and 1 B. In that situation, I have 2 possibilities, A, B, and BA. So these are the only 2 permutations that I can write down for these objects. And there is no direct formula or direct notation for denoting the number of permutations if the objects are repeated. You need to consider them case by case and add them, yes, so using the sum rule. But at least for this case we will have a formula. So is everything clear for everyone, that what is the meaning of an R permutation if you have more number of objects? Okay, so let me test your understanding. So what do you think? Yes, any questions?
Did you say that?
May you please speak louder?
Can you hear me? Hello?
Hello, yes?
Yeah. Did you say that we couldn't use the formula for repeated letters?
I'm not saying there is no known formula for that, because you have to consider case by case, yes?
Okay.
Yeah, but for this one we will have a formula if the objects from the beginning are distinct, but if the objects are not distinct, I mean, you cannot control the problem because the number of possibilities quite be different. It could be quite different, so you need to consider them case by case. Okay, so let us go to this problem. What do you think about these numbers? Of course, in the next theorem you see on top of here, I will give you the formula. But without having that formula, in principle, you should be able immediately to tell me what are these numbers. Assume that n is a given natural number, 10, I don't know, 15, whatever. And I want to calculate p of n and 1. So what would be the answer? What is your prediction for the answer to p and n and 1, and the same p, n, and n? So let me just concentrate here. If any one of you wants to answer this, please let me know. And then what about this?
Are the answers n and n factorial?
Yeah, very good, very good. Yes, thank you. So it means that you understand actually what's going on. So what is the meaning of p, n, and 1? Here it means that I have n distinct objects. I want to write all one permutations and count them. What is a one permutation? It means that I choose one object and arrange it. There is no arrangement if I just choose one object. As soon as I choose my object, the arrangement is already done because I have only one object in my hands, yes? And then I have n objects. So in how many ways I can choose one object from the n objects? It is n, yes? So clearly the answer to this should be n. If there is some questions, please let me know. And now here I have n distinct objects. I want to choose all of the n objects and arrange them. So actually I am facing a problem that I already know how to solve. I have n objects. I want to arrange them because when I choose all of them is now in my hand. I want to arrange them. So there is n factorial ways to arrange that. So we can predict immediately that the answer to this should be n factorial using the formula that we will discover shortly. Is that understandable for everyone? Good. Now let us go to the theorem. The theorem, this formula is given in the formula sheet, and there is a button on your calculator. You need to find it out. It is probably different from calculator to calculator, that you can use those buttons to immediately calculate this combination, okay? Let n and r be natural numbers such that r is between 1 and n. Then p, n, and r is equal to n factorial in the numerator and the difference between these two numbers factorial in the denominator. Okay, the proof of this is very, very simple. So what is the proof here? If we want to have a proof, it's better to understand the proof, yes? So here, how many objects I have? I have n objects, and the objects are distinct because I told you that this notation is only used when the objects that you have are distinct. Okay, so here I have n objects, a1, a2, and say an. I have n objects. Let me call them a1 up to an. But how many places do I have? I have r positions. I have r places somewhere between 1 and n. Okay? So for example, I have r positions here. So let me call this one position 1, and then position 2, position 2. Let me write position 3, and finally I will have position r. Yes, so let me write the numbers inside. So position number 1, position number 2, 3, and up to r. So what is my duty? My duty is to choose r of these objects. When they are in my hand, go there and arrange them there. Okay? I can use the product rule to answer this immediately. Okay, can you tell me, let me consider this stage 1. How many options are available for stage 1?
R options.
No, be careful. How many objects do I have?
Objects.
Yes, I have n objects. If the arrangement is done, it means that the first position is filled with one of these alternatives. Yes, because I have n alternatives, so this means that I have n options available to fill up the first position. Now that the first position is filled, when I go to the second position, because I'm not allowed to repeat, so how many options are available for the second position? It's clearly n minus 1. And how many options would be available for number 3? Because now I have replaced 2 of my objects in position 1 and 2, so there are n minus 2 left for me. Okay? And if I continue this way, can you tell me how many options would be available for the last one?
In factorial.
No? Why in factorial? No, but I think I'm confusing you. I have n objects. I have r boxes. Each box can be filled with at most 1 and shouldn't be left empty. Okay? How many, so assume that these are marbles, I don't know, labeled marbles. How many options are available to fill the first box? I have n options available. I can choose any one of these marbles and put it in the first box and close it and put it aside. And then I go to the next box. How many marbles are left now? N minus 1 marbles are left, and I have to choose one of them because each box should be filled with exactly 1 marble. So I have n minus 1 marbles available. I can choose any one of them. So for the second box, I will have n minus 1 options available. For the same reason, the third box will have n minus 2 options available. What is the number of options available for the last one, or the last box, rth box?
1.
No. If r is equal to n, you are right. That would be 1. But the numbers are different. Pardon? No, again, not correct. It has a very small flaw in it.
Is it n minus r plus 1?
Exactly, n minus r plus 1. Thank you. Yes, because you see, if the position, so you see the first one is n, the second one is n minus 1. The third one is n minus 2. So the number that you are subtracting here is 1 less than the number of this, the box number, yes? Here the box number is 1, but you are writing n. N means n minus 0. Here this is the second box, but you are not writing n minus 2, you are writing n minus 1. Here this is the third box, so you are not writing n minus 3, you are writing n minus 2, 1 unit less. And now that this is the rth box, you shouldn't write a minus r, you shouldn't write a n minus r minus 1. This number should be 1 unit less than the box number. But then, as you said, when I multiply this negative sign inside, it becomes n minus r plus 1. And the answer you provided is completely correct. So this would be n minus r plus 1. I hope that everybody agrees with me. If not, please let me know. Okay, so the total number of ways that I can do, so it means that the question mark here, p, n, and r, is equal to the product of these numbers, n times n minus 1 times n minus 2 up to n minus r plus 1. By the way, some books just write this as the formula for p, n, and r, which is of course correct, but I would say that this is easier to remember and it's more compact. Okay, but how can I go from this to the formula here? Can I say that this is n factorial? Not yet, because n factorial means that I have to start from 1 to 2 to 3 and go up to n. But there are some of these terms missing here. So here this is not 1, yes? In general this might not be 1. So if I want to continue, it means that I can rescale it in this way. Yes? What I do, I multiply it by n minus r, I multiply it by n minus r minus 1, and I continue until I reach to 3 to 2 to 1. And then divide by what I have multiplied in order to compensate for the multiplication. So this would be n minus r minus 1, and this will continue until 3, 2, 1. So let me just wait to see if that's understandable. First of all, this equality is valid because what I have multiplied, I have also divided. So this means that this one and this one are totally gone, and then I will get the same expression back, so that's correct. But what is the benefit of doing that? If I ask you what is the denominator is the product of consecutive integers starting from 1 up to this point n minus r. So hopefully you agree with me that the denominator is nothing except n minus r factorial. And now look what is happening in the numerator. The numerator is the product of consecutive integers starting from 1 going up 1 by 1 until I reach to n. And that is n factorial. And that is the compact formula that actually you have it in this theorem. Is that understandable? Okay, good. So this is a very important formula. Let me consider this remark as well. If I ask you what is Pn of 0, you might say this is not sensible, because Pn and r means that I have n distinct objects, I want to choose r of them and arrange them. So in principle, Pn and 0 doesn't make sense. This means that I have n objects, I don't want to choose any of them and arrange them. But this is by convention also defined using the formula itself, even though if someone asks you, do you have any combinatorial argument behind this symbol, you would say no. But if they ask you, is this symbol defined, you would say yes. And the definition is using this formula. So if someone asks you calculate Pn and 0, by convention it is defined to be 1, and that's a good definition because it squares with the formula itself. If I ask you what is Pn and 0 using this formula, you put n factorial in the numerator, and then you write n minus 0 factorial in the denominator. But n minus 0 is just n factorial, and n factorial and n factorial are gone, so it is 1. So it is a reasonable definition to define it 1, but there is no combinatorial argument, there is no combinatorial understanding behind this number, because I have n distinct objects, I want to choose 0 of them. In how many ways I can do? It might be you say that I can choose it in one, I can do it in one way, not to choose it at all. But it needs to be defined. So Pn and 0 is defined. So be on the safe side. This formula is valid if r starts from 0 as well. Okay? And then let me calculate Pn and n that we had above here. So let me, by the way, that's a good exercise. Let me change my color and write something here. So assume that you now know the formula, Pn and 1. If you want to, of course we were able to answer, the answer was n, but let me use the formula now. So the formula tells me to write n factorial, and then you write n minus 1 factorial, but you know that n factorial can be written as n times n minus 1 factorial divided by n minus 1 factorial. Whatever this number is, this is cancelled from the numerator and the denominator, and the answer you predicted without knowing the formula, you see it's correct now, and that is n. But let me calculate the same thing here. So you see, this is what I wanted you to understand. So Pn and n, if I want to calculate it, it becomes n factorial and then n minus n factorial. So this becomes n factorial divided by 0 factorial. This is on the one hand using the formula. On the other hand, based on the definition of this symbol, you realize that this should be n factorial. So what happens when this expression becomes n factorial? This expression becomes n factorial if the denominator is 1. And that is the idea behind this definition. It was a little bit strange. Do you remember when I wanted to talk about factorials, I defined 0 factorial to be 1. Okay, and that is the reason. If we define 0 factorial to be 1, then I don't need to separate cases here. I would say that this also works for the case where r is n. Otherwise, I should say that this formula is valid from 1 up to n, but not equal to n. And for n equal to n, I have another formula. If I do not choose 0 factorial to 1, this formula should be written in 2 different ways. One for the case where r goes from 1 up to n, another case for the case r is equal to n. Yes? In those cases, because I do not want to make trouble for myself, I will, by convention, define 0 factorial to be 1. So this is a good understanding of why people define 0 factorial to be 1, not any number, any other number. And that is the content of this remark, so you can read the remark later. Any questions? Okay, so one thing that is very important, when do we use this formula? Okay, we use this formula if we have n objects. I want to choose r of those objects and arrange them. The total number of choices and arrangements is important for me. Okay? Okay, so let us solve these problems. How many 4-letter words can one construct using the letters in the word keyboards? Okay, so we want to construct 4-letter words. So how many letters are there? 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then you see that all these letters are distinct letters. Okay? So, when you say, I told you before, how many words, it means that you don't need to be worried about if the word is pronounceable or is it a meaningful word or whatever. So it means that I am only interested in the arrangements, and we know in principle if I interchange the letters in a word, I will probably have a new word. By the way, I think the English word for it is called anagram. Yes, anagram. So for example, listen and silent are called anagrams. Of course, anagram means that the words should be also meaningful, but in combinatorics we don't care about these words being meaningful. Okay, we just consider mathematical or combinatorial anagrams. Okay, so how many 4-letter words can one construct using the letters in the word keyboards? So this is the standard use of these R permutations. Here, how many distinct objects? So the question mark should be clear for you. What is that? This is P. I have 9 distinct objects, my letters, and I am interested in choosing 4 of them and arrange them. So that is the number. Okay? So this is the number. And I know how to calculate it if I really want to do that. According to the formula, 9 factorial goes to the numerator, and the denominator should be the difference between these two numbers, 9 minus 4 factorial. So let me calculate it until the end. Okay, so it becomes 9 factorial, and then 9 minus 4 is 5 factorials. Yes? And then you know how to do that. So it becomes 9 times 8 times 7 times 6 and times 5 factorial, and then you divide it by 5 factorial. Yes? And this 5 factorial and that 5 factorial are gone. Let me just use my calculator to calculate this. So this is 9 times 8 times 7 times 6. So it is 3024. But most of the time I am not interested in the real final number, because that would be just putting these numbers in your calculator. For example, if I don't ask for the number in the exam, if you just write this answer, that's enough. Any questions? So the important thing is that you should realize when you are allowed to use this formula. Okay, for example, let me solve another problem. How many 5-digit numbers with distinct digits are there? By the way, let me just mention, if someone in the exam solved this problem from scratch, that's also okay. So you would say that, okay, for writing a 4-letter word, I need 4 positions, and how many ways I can fill this first one up? I have 9 options, and then I will have 8 options, 7 options, and 6 options. You see, the answer is exactly this number here. But I want you to learn that, because this will help you. If you want to solve everything from scratch, for harder problems it becomes very hard. So it is important to realize when you are allowed to use this formula. Okay, how many 5-digit numbers with distinct digits are there such that each of them starts and ends with an odd number? Okay, so how should I do that? So here I have a 5-digit number, so it means that I have 5 positions. 1, 2, 3, 4, and 5, yes? But the first one and the last one should be an odd number. So let me write all the digits that I have. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, the first stage of the problem is to fill up these 2 positions. They have to be odd numbers. Okay, but how many odd numbers are available? 1, 2, 3, 4, and 5. I have 5 distinct objects. I only want to choose 2 of them. An arrangement is important, because in writing numbers it matters which number you write first and which number you write the second. So everything is exactly according to the theorem that we just learned. So the first stage of the problem is P 5, 2. Yes, I have 5 distinct odd numbers. I want to choose 2 of them and fill up this one and that one. Okay, now 2 of these odd numbers are gone because I am not allowed to repeat digits. The digits should be distinct. So this means that, let us for example assume that I just use, for example, 1 and 9 in some arrangement in the first position and the last position. Okay, and then how many positions are left for me? There are 3 positions left for me. And how many numbers are left for me? 1, 2, 3, 4, 5, 6, 7, 8 numbers. All of these 8 numbers are distinct. I need 3 of them, so I have to choose 3 of them. Still, I can choose the odd left ones, the left odd ones. Yes, 3 and 5 also can be chosen, no problem. So in how many ways I can choose this? I have 8 objects, and then I choose 3 of them, and then I have to multiply them. So that is the answer to this problem. Yes, this is the number of ways that I can choose 2 odd numbers. After the first stage is accomplished, I accomplish the second stage, means filling these numbers in these different ways. I want to accomplish all the tasks, so it means that I have to do the first stage and the second stage after that. So it means that I have to multiply these 2 numbers. So what I expect you to write is this. Is that understandable? Of course, you can start everything from scratch. That's also correct. Okay, So I will give you two more examples. They are very related. The reason is that from psychological point of view, one problem is easier for us to understand than the other. And we had this before. In how many ways can 5 students be chosen from 15 students and be seated in 5 numbered chairs? So it means that the chairs are different. So in how many ways I can do that? This is immediately according to what we understand from this R permutations. I have 15 distinct objects, here 15 students, but I don't want to choose all of them because I have only 5 distinct chairs. I want to choose 5 of them and arrange them. So that is exactly this problem. I hope that you agree with me that the answer is P15 and 5. Yes, there are 5 chairs. Is that understandable for everyone? That would be the answer to this problem. Okay, let me change the scenario a little bit. So this is a good experience to know. Example number 10. In how many ways can 5 students be seated on 5 chairs out of 15 numbered chairs? So here I have 5 students. Do you remember we had this situation before? I have 5 students, but I want to distribute them in 15 numbered chairs. Okay, so this might be seems a little bit different, but you would see that the answer is exactly the same. Why is that? Because you would say that how many chairs are available now? I have 15 chairs, so chair number 1, chair number 2, up to chair number 15, yes? So this is chair number 1, 2, up to 15. How many options here are students? I have 5 students. So I would say that how many chairs are available for the first student? The number of available chairs for the first student is 15. But now one of these students take one of these chairs, and then how many chairs would be available for the second one is 14. Yes, the next one will have 13 options, the next one would have 12, and the next one finally will have 11. So definitely this is the answer. And by the way, you see that I just used the product rule without any further knowledge. But I want you to be able to use these notions, these new notions. Okay, but do you agree that this is the same answer? Yes, because let me go back and calculate the previous problem. You see, here if I want to calculate this according to the formula, it becomes 15 factorial divided by 15 minus 5 factorial. But this becomes 15 factorial divided by 10 factorial. And then in the numerator you can write 15 multiplied by 14 multiplied by 13, 12 and 11 and finally 10 factorial, and then divided by 10 factorial. And then you see that this 10 factorial, whatever it is cancelled, and what you get is exactly the answer that you get for the other problem. Yes, it was very easy for us to understand that the answer to this problem is P of 15 and 5, but it might be a little bit harder for us to understand that the answer to this problem is again the same. It's P of 15 and 5. Okay, so this I want to write it as a remark, and I want you to know about that. So let R and N be natural numbers where R is lying somewhere between 1 and N. As the last two examples show, the number of ways that one can choose R objects out of N distinct objects and arrange them in R distinct locations. This is one scenario. And the number of ways that one can arrange R distinct objects in N distinct locations are both equal to Pn and R. Okay, so remember that it doesn't matter if you have more room than the number of objects, or you have more number of objects than the number of positions. If you want to choose the objects and put them in a smaller number of places, or if you want to choose a smaller number of places and fill them with some objects, they are the same number. The number of ways that you can do them are both equal to P, N, and R. So that is what I want you to understand. Any questions so far? So let us solve more interesting problems now. I'm saying that all these problems that I'm mentioning here, you can in principle start using from scratch, using the product rule. But I want you to start using this new notion of R permutations as much as you can. Okay, so let us start solving these problems. Using the letters in the word magnetic, how many 5-letter words can one write down such that in each of them both of the letters M and N are used? Okay, so do you have any idea?
Is it P8 and 2 times P6 and 3?
So can you motivate that? So I have to write it down. So magnetic. So let me write M and M, G,
So there's 8 total letters,
yes.
and I have to choose 2 of them, just being M and A.
Okay.
And then the rest. So after that, I have 6 letters.
Okay, but so may you please tell me your answer, because I don't. May you please tell me your answer? You are saying that P of what?
Or maybe I've made a mistake. Let me think about it.
Yeah, it needs a little bit of thinking.
Is it
Yes.
Is it the P? Or who do you want to answer?
Yes. You just tell me.
You can answer yourself.
Is it P5 and 2 times P6 and 3?
If you mean this, I don't know. I need to listen to your reasoning, because I think the way that I want to answer it is different. What is your answer, Khulud? Is this the same answer?
No, I had a question. Can you make them adjacent?
No, the letters are used. You can have a different strategy. I have to listen to that. I cannot say that whatever you are saying is. So what I am understanding from this question is that M and A should be used, but not necessarily adjacent.
Adjacent. Okay.
Yeah.
So it solved the question and make them adjacent, then it's wrong.
Yes.
Right?
Because that is only one portion of that. Yes.
Yeah. Okay.
Yeah. Don't push these. You need to exactly what you read. You need to follow exactly the instruction. If they want to make M and A adjacent, they definitely mention it. If they don't mention it, it means that there is no constraint. They could be adjacent or not. Okay, but let us see if this is the correct way of counting. So what was in my head? I was thinking, assume that I want to do this. Yes? 5 letters, so I have to, so sorry, I have to clean 3 of them. Is that your concern?
No, it wasn't my concern. I think they have a answer, but it might be the same as.
No, just tell me your answer. I can write it down.
So I put P6 and 3, because that's 3.
Yeah, just tell me your answer.
And then we want to 5 times 6. Let's see. Yeah, something like that.
Okay, so let me
No, not times 6. Yeah, no, something like that. Yeah.
Okay, so let me see what I was thinking. So here, when I read the problem, I understand that I have to have A, M, and A. So it means that from these 5 positions, 2 of them are related for A. Here, I have more positions available than my objects.
No, I meant times 4 times 5 because that's how many positions. Right?
Okay. Let us see. Let us see what happens. Here, when I read the problem, I realize that I have to use M and A. Yes? And now I would go and choose 2 positions for M and A. This is, I started in this way, okay? Then I have 5 positions. The number of positions is more than the number of my objects, but according to this remark, I don't need to be worried about that. I have 5 positions, and then I have 2 objects. I want to arrange them. So as you said, that's correct. So I think, yeah, you are correct because I was thinking in a wrong way. I think your answer is completely right. Yes? Yes, your answer is completely right. This answer is correct, but this answer is not that answer. You said 4, let us come back to this. So this answer that you said is completely right because you are saying that you have 5 positions, but you have 2 objects. You want to choose 2 positions for your objects and put them according to this remark. It doesn't matter. The answer is still this. And then 2 of these positions are now gone. For example, this one and that one. For example, you choose to put M here, A there. This is one scenario, of course. And then how many positions are left? The positions are 3, but the number of objects available, M is gone, A is also gone. So here, the number of objects is more than the number of positions. But it doesn't matter again by that remark. So exactly what you said is correct. So how many objects I have? 1, 2, 3, 4, 5, 6. But how many positions are left? 3. So then it becomes P, 6 and 3. And then hopefully you realize that you have to multiply them, not to add them. So that is the correct answer. So and then so I think you corrected it later, Alex, because now this number is 5 factorial divided by 5 minus 2 factorials. So it becomes 5 factorial divided by 3 factorial. And now what you said later is correct.
5 times 4.
Yes.
Yeah.
So but you solve one part of it using the formula, one part of it using the product rule. Even if you solve all the problem using the product rule, that's okay. But I want you to improve your understanding about these R permutations. So I myself prefer, so even though your answer is correct, if you write it that in the exam, that's totally right. But the first answer, I prefer the first answer myself here in this lesson. Okay.
I was thinking about possible places where you can insert.
Yeah, you can start everything from scratch, but I want you to understand this one. I just want you to, in this lesson at least, I emphasize on writing this. So you see, this is a very good problem, because it is using this remark effectively. For the first part, the number of locations is more than the number of objects, but immediately in the same problem for the second stage, the number of objects is more than the number of positions. But who cares? According to this remark, and I motivated you in the previous 2 examples, that both of them can be counted in the same way. And then using the product rule, I have to multiply them. Let us go to the next problem. If you have any questions, please interrupt me. So how many permutations of the letters of the word second are there such that the vowels are in even locations? I hope that you understand what I mean, yes. So here, 1, 2, 3, 4, 5, 6. We have 6 positions. So let me write this down to make sure that everyone understands. So we have, I need 6 positions. But I want to put the vowels in the even positions, yes? What does it mean? So it means that, for example, if this is position 1, 2, 3, 4, 5, 6, then you understand what I mean. So for example, the second itself is a good one, you know. You see, I have two vowels in the word second, and they are on even positions. For example, I can write this one. This is also good. This is a permutation in which the vowels are still in even positions. Okay, you understand what I mean now, if the sentences are not that clear. So what would be the answer?
Would it be P32 times P44?
Yes. Or instead of P44, what can I write?
P4 factorial.
Yeah, 4 factorial. I will go for 4 factorial here, even though P4 and 4 is also correct. So yeah, that's right. So you are saying that I have only two vowels. So objects are 2. The positions for the vowels are even positions, 2, 4, and 6. The number of positions is more than the number of objects, but we have now enough experience. So the answer for the first step would be 3 and 2, P of 3 and 2. And then 2 of them are now filled with the vowels. For example, assume that we chose this for O and we chose this 6 for example, E. Then how many options are available? How many positions are there? 4 positions. And how many objects are left for me? Exactly 4. So that is the previous lesson. 4 objects, 4 distinct places. I would prefer to write 4 factorial, but if you write P of 4 and 4, that's also correct. So I would multiply it by 4 factorial. But let me just make sure that you understand that we have to multiply, because this task is accomplished after both of these stages are done. And then this 4 factorial, let me just repeat it again. This number is independent of how I have done the first step. Why? Because it doesn't matter if I choose this and that for E and O. I have 4 factorial left for me, 4 factorial ways to do the second stage. If I have chosen, for example, 2 and 4 and put E here and O there, I see that there are exactly 4 positions left and 4 objects left. So this 4 factorial is independent of how I do the first stage. This is always important to check to prevent double counting. So that's the answer to this problem. Let us go to the next example. This is a much more interesting, a little bit harder problem. So how many permutations of the numbers 1, 2 up to 9 are there such that no 2 of the numbers 1, 2, and 3 are adjacent? So it means that if 1 and 2 are here, 3 is there. I don't want to count it because 1 and 2 are adjacent. If 1, 2, 3 are next to each other, I don't want to count it because all of them are adjacent. So I don't want to have any pair of these 2 numbers adjacent. I want to count the whole possibility. This could be quite hard problem if you don't know the trick or can design a nice way of counting this. Let us discuss it together. I want to hear from you. Do you have any strategy to tackle the problem?
Maybe we try to calculate the total number of permutations and then subtract.
This is the first thing comes into mind, and that is correct. I'm not saying this is incorrect, but that would be horrible, yes? Because if I ask you, what is the total number of permutations, you know that. I have 9 objects, the total number of permutations is of course 9 factorial. What do you want to subtract from it?
The numbers where 1, 2, or 3 are adjacent.
You see, there are many different options. That's what I'm saying. If you get this feeling, I calculate the number of items where 1, 2, and 3 are next to each other and subtract that number from this, then it is not correct. Yes, because when you count, so if let me tell you, can I count the number of permutations in which all 1, 2, and 3 are adjacent? So let me just write it down. 4, 5. Let me write and then clean it because that's not part of the problem. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Yes, do you remember we can easily count this way of doing so I put them in a box, I consider it one box, then how many objects I have? 1, 2, 3, 4, 5, 6, and this 7 objects. So I would write 7 factorial, but these can be arranged in 3 factorial ways. So this is the total number of items in which 1, 2, and 3 are all adjacent. And then when I subtract this, I hope that you understand this is not the correct answer for this problem. Yes? Because here I have subtracted only those items where 1, 2, and 3 are all adjacent. But what about this? 1, 2, 4, 5, 6, 7, 8, 9, and 3. In this subtraction, this is excluded. So this is still there, which I don't want to have it because now 1 and 2 are adjacent. So I want you to understand, if you calculate it in this way, you are subtracting the items in which all 1, 2, and 3 are adjacent. Of course, that is one part. That is not completely wrong. I want to exclude them. That is right. But there are more items still need to be excluded. For example, one of these items is this one, which is not excluded here. One way is, of course, to consider all different scenarios. And this is called exclusion-inclusion principle. But this is beyond the scope of this lesson. And even if you know about that, using that is a little bit hard. Here we have a much nicer strategy to solve the problem without making it so hard. Exclusion and inclusion principle is the more advanced complement rule. Yes, but this is not part of your lesson, so don't worry about that. But at least I want you to understand this answer for this problem is wrong. If you don't understand this, ask me to repeat it again. Okay, so hopefully good that you understand this. So let me erase everything now. Let us try to hear from you. Do you have a strategy here? This would be our last problem.
We're not interested, isn't that the permutations of where the ones where 1 or 2 are adjacent, 2 or 3 are adjacent, or 1.
No, if you want to cook up this strategy, I told you it will work, but you need to be very careful. Yes, and that is inclusion. There are many technical things to do that. I can talk about this. It is not beyond your understanding, but let us not to do it in that way. Okay, so because this is an important...
Select.
Yeah, yes?
I'm just thinking, if we start by selecting locations for 1, 2, and 3, we can guarantee that they will never be together.
Okay, so let me you see these two problems, number 13 and 14. You can consider these as homeworks. Try to work on them. I will of course post this to the YouTube below the video, but you can just have a screenshots from these two problems because it takes a little bit longer time for the YouTube to process the video. But you can consider these two problems as homeworks for I don't know, for Thursday. Yes, These are nice problems and they are very similar. The difference is that here I have some letters repeated, so objects are not totally distinct, but here my objects are totally distinct. There is a strategy to tackle this problem, and it doesn't care about repetitions. You will see that this will solve the problems in two cases with the same strategy. Pardon?
With the strategy I described, like first selecting the positions for 1, 2.
Okay, just do it and find a number and bring your number next session. We will start with you, okay? And then continue solving that. Yeah. Did you take the screenshot? Because now I want to stop this sharing.